Welcome to the CRC seminar series organized by Technology Innovation Institute Abu Dhabi. It is my pleasure to introduce the guest speaker for today's session, Professor Itamar Levi. Itamar Levi received his BSc and MSc degrees in electrical and computer engineering as a part of the Direct Excellence student track from Ben Gurion University in 2012 and 2013 respectively. He completed his PhD at Bar Ilan University in 2017. He was a research associate in UC Louvain, Belgium until 2019 with the UC Louvain Crypto Group, where I had the privilege of working beside him. Currently, he is a computer engineering faculty member at Bar Ilan University in Ramat Gan, Israel. He is also a member of the Emerging Nanoscale Circuits and Systems Lab at BIU. Dr. Levy's current research interests are digital circuit design, embedded system security, security evaluation analysis for cryptographic devices, side channel and fault injection countermeasures, and cryptographic implementations. As, as part of his activities, he has co-authored over 50 journal articles and international conference papers and has 7 patent applications. He also has co-authored a book on dual mode logic, a new paradigm for digital IC design, and serves in the technical committees of IEEE Circuits and Systems Society and hardware security venues. Before we start, I would just like to remind the participants that we have a Q&A button in which you can directly ask your questions to the speaker, which he will either address during the talk or maybe later. So, Itamar, the floor is yours. Thank you.
So, thank you, Kashif, for this thorough and wonderful introduction. And I'm very happy to talk here in the CSC seminar. Well, we're just 1 hour away, so good afternoon to everyone. So, today we'll talk about side channel analysis attacks security and security mechanisms, and about a type of an attack which is directed toward masked designs. And I will talk about the connection between the two. So I will not repeat Kashif's wonderful introduction. So I'm from Israel, and I did my bachelor and master's at Israel, and also my PhD, did my postdoc at Belgium, and now I'm an assistant professor at the Bar Ilan University in Israel. So the outline of my talk will be to first start with some general motivation to side channel analysis attack security. I will discuss a unique low cost and ultra low effort CAD compatible, that is computer aided design compatible side channel security countermeasure. Basically, it is a randomization mechanism which is very efficient and can be implemented with standard digital design tools. I will talk about an improvement to this construction, and then I will move on to another topic, which is externally amplified coupling attacks. This is an attack which is directed toward masked designs, and there is a connection between the two parts of my talk. That is the first mechanism that I will lay out is efficient to counteract this type of attack on masked designs. I will finish with some conclusions. Okay, so let's start with the general motivation. So it is well known that information is leaking from the processing of internal variables or internal computations in cryptographic designs. And it is also well known that the success rate of an attack depends on the abilities of the adversary, the resolution of the adversary. This basically implies that if an adversary can look with higher resolution or to smaller regions, he can bypass mechanisms, and he can also bypass what is denoted as algorithmic noise. So taking a simple example, if you see here this gray box, and we have some secret value or secret key, typically these keys are chunked up into subparts. And if we look on a side channel adversary, which measures the power consumption or current dissipation from that device, then the current will be a summation of the leakages which are affected by all of those components. However, there are adversaries which are more local. They can approach the device with a very local sensor, electromagnetic sensor, for example, and by that they can access electromagnetic radiation from just one subset of the key. And by that, they can actually eliminate noise or reduce the noise level or the algorithmic noise of the device, and then succeed in their attack much easier or much faster. So locality-driven countermeasures, that is countermeasures which can be embedded locally, are very important while considering this type of adversaries. Okay. So there is a long line of research up to this point, which already reveals that protocol or mod level security is expensive. For example, if you will do ultra fast rekeying, you will rekey your device very often, then clearly to some extent you will eliminate the side channel issue, which collects measurements on a certain key. However, the communication cost of doing that or the randomness cost which required to generate keys will be very high. However, still, current proposal, both for lightweight crypto and both for other type of cryptographic constructions, do implement rekeying heavily. However, the assumption is that when we do consider a side channel adversary, we will need at least to protect our device strongly against SPA security. That is, we need to embed some security mechanisms on leakage carrying signals. So there are several options to do that. We can look on circuit or architectural solutions. These are typically very heuristics. For example, you can look on Mendeling the time domain. For example, there is a software shuffling where you shuffle the execution time of an operation, or you can randomize the amplitude of a device. Alternatively, you can also utilize the space domain and randomize the space, the location of the computation, where it is being taken place. However, all these circuit or architectural solutions, they provide quite low level of security. That is, they provide a linear adversarial complexity factor as a function of the security parameter. So if your security parameter is the time or amplitude variance, you will only get some linear security factor, which is not much. And also their cost is linear in latency, in energy. Therefore, some other solutions were proposed throughout time. For example, mathematical or variable representation solution. You can take an example, Boolean masking. In masking, what we do is we split sensitive variables into two shares or sections. where d minus 1 of these variables are drawn randomly. You can look on the equation to the top right part of the screen. And then you compute the last value, xd, if you have d minus 1 random values, xd by the XOR combination of all those values with the secret. Now you will get a secret vector, which none of its elements directly contain the secret x. And this, and by doing that, adversary which measures the leakage will never get some correlation to x. He will get something else. He will get correlations to those random shares. So let's take an example because we will utilize it later. If we have a secret value x and we used masking with two shares, that is, the two shares are x1 and x2, then one of the shares is R, random, and the other one is R XOR the secret, X, so x2. The leakage of these two blocks, which process or stores the shares, is assumed to be additive. The leakage is the summation of the Hamming weight of the first share plus the Hamming weight of the second share plus some noise. And if we draw the conditional leakage distribution while conditioning the secret X, we will get that when X is 0, we get this red curve distribution, and when it is 1, we will get the black curve distributions. And what it shows us is that the mean of these conditional leakages is in both cases 1. It is the same. So the first statistical moment of the leakage does not reveal any information on the secret. However, the standard deviation or the variance of those leakages does contain information on the secret variable. However, it enforces an adversary to estimate the second statistical moment, which means you will need to collect more leakages. Okay, you need a longer side channel attack campaign. Now, this is quite nice because it scales up to any D statistical moment. If you want to force an adversary to estimate the third or the fourth or the fifth statistical moment, you will need to share across 3, 4, or 5 secret values vectors. However, naturally, as you move on to representing your secret with vectors, computations become expensive. So area and energy is quadratic with D, with the level of sharing. And the randomness which is required for that process is also very large. So masking is highly expensive if you want to address high security levels only with masking. And an important property relating to masking, which is already known from 1999 by Chari et al., is that the security of masking or the number of traces you need to attack a mask design grows exponentially with the standard deviation of the noise at the base, where D is the exponent. So if you want to gain more security, you need to increase D as much as needed, okay, according to the standard deviation or the SNR of your device. Now, this is an important property which we will use in a few slides. Instead of increasing D, which we know that its cost is quadratic for masking, we can first introduce a larger noise in the design, that is, reduce the SNR of the design, of the internal blocks, of the shares, and only then mask. By doing that, perhaps we can find a mechanism which in total will cost much less. So I'm coming back to this point. Okay, so after this motivation, let's start with the first part of my talk, a unique low-cost computer-aided design for side channel analysis attack security. This is based on a work which I had with Davide Belizia, David Ball, and François Xavier Standard. Okay, so what do we want from a randomization mechanism, from a leakage randomization mechanism, which will be embedded in our hardware? We want it to be CAD compatible, that is easy to be used in standard design flows of IC chips, of integrated circuits. We want it to have very low electronic cost, and we want it to be agnostic to the underlying logic. That is, it doesn't need to be matter what logic is underneath the randomization mechanism. Moreover, as I started to discuss a few slides ago, locality is important to resist, for example, electromagnetic side channel adversaries. We want our mechanism to be embedded locally for each local block in the design. And of course, if we add something which randomizes the leakage, the best that we can get is if the leakage will be distributed uniformly, okay, if we want to achieve maximum entropy. Okay, so our solution is a concept which is based on resistive DACs, or resistive digital to analog converters. So basically what you see on the left side is standard digital to analog converter circuitry, where you insert a random sequence, a digital sequence of zeros and ones. This sequence of zeros and ones selects how to connect bits, the switches that you see on the blue side, where each bit is modulating the output voltage of the circuit. So you have two rails, VDD and ground, and by selecting the configuration of which bits are connected to VDD and which bits are connected to ground, you can actually modulate the output voltage of the circuit. So between the range VDD and ground. So this is a digital to analog converter. You get a digital sequence and you convert it to analog voltage. However, in order to do that and to abide a uniform separation, a uniform quantization of the space, the sizes of these resistors needs to be a series, okay, a series with powers which are relative to the bit index. So a resistance of 1, 2, 4, 8, 16, etc. So we wanted to utilize this mechanism in a standard digital design flow. So what we have in standard digital design flows is something which is denoted by power gating cells. And power gating cells are elements which are typically used to power gate a logic block. For example, if it is turned off at the moment, if it is not needed, if you want to save power. And what we did is we placed a series of parallelly connected bank of power gates, where each one of those is upsized with the same upsizing values. And so, and the inputs to those power gates are the digital sequence of bits. And by that, if we place this mechanism between the general power supply of the circuit into the logic block underneath, then we can actually modulate the effective power grid resistance, which will imply that we modulate the leakage, the current. And the whole agenda is to be able to generate a uniform leakage distribution. So we want this mechanism to generate uniform leakage according to the input digital values. These are values. Okay. Now, however, you can think that maybe if these values are random because we are randomizing, then if R vector is the 0 word where all bits are 0, is the 1 word where all bits are 1, then the power grid to the device is disconnected. This is an issue. So what we need to add is we need to add an always on device, which we call a bias, which is always open. Okay, and this element in blue is making sure that there is always current flowing to the device. And we need to upsize it to provide enough current or enough energy to the block. Now, the question of the size of this device is very important, and I'm coming back to it in the next slide. However, already now we can clearly see that in order to achieve a uniform leakage distribution, we only need a couple of power gating cells. Now, the cost of this is very, very, very low, okay? Especially when you compare it to the logic block which they try to protect. So it's only a few percent from the total area of the device or the total energy, which means we can get a very low cost EDA compatible or standard flow compatible randomization mechanism. In the previous, it was assumed that randomization in hardware will be very costly, but it is a misconception because it assumes that you achieve randomization by duplicating the logic block. And in that sense, yes, achieving leakage randomization by duplicating logic and asserting random values will be expensive. So this is our alternative. So size does matters, and I will come back to the matter of the absolute size of this construction. So what we did is that we generate randomized power grid or randomized resistance for the power grid achieved by standard cell power gating cells. And to the figures on the right, what you see is the randomization mechanism while it is working. The x-axis is the time domain, and the randomization mechanism and the y-axis is the current in this figure. And as we go along throughout time, we actually switch the randomizer to a different state. And as it is possible to see, the modulation of the effective resistance or the effective current is uniform because the trend is quasi-linear, so it is quasi-uniform. Also, the voltage drop across this resistor or effective resistor. Okay, so now the main novelty or the main benefit of this mechanism relates to the fact that it is CAD compatible. We can embed it into any digital integrated circuit. We do not need any specialty in analog circuitry design. It can all be done in RTL, in Verilog or VHDL if you want, and it can be embedded by electronic design automation tools. So what you need to do, or what we have proposed, is that we need to first divide the entire core into small partitions. For example, here you see an AES, the standard for now, encryption core. So we partition the entire encryption core into sub-blocks, which only depends on a subsection of the key, or on a byte or 16 bits, for example. And then we will embed this randomization mechanism for each one of those blocks locally. Now, this partition is done in Verilog or VHDL. So it is inserted in RTL, in the RTL. And then when we want to actually embed those randomizers to resist localized adversaries, electromagnetic side channel analysis, we can actually add those, because these are synthesized modules, we can add those in RTL directly, write them, okay, in code, or we can actually add those with a script. Okay, so very easy, very standard, very, no expertise is needed. Okay, and after that, we will move on to the physical design, to the backend flow of the chip. We will take those partitions and we will partition the core and use power domains. So each block that you see here is a power domain. For example, the left column contains power domains of all the S boxes, and then mix column and switch rows and the key handling, etc. And for each one of those blocks, we are adding our randomization mechanism in the backend flow. Now, the tool does that automatically. We can use common power format flows, which are standard, which are used in the industry today. And this is the main benefit of the mechanism. You do not need any specialty knowledge or analog level interference. Okay, so backend is natural, as I said, and let's look in a zooming view on one of the blocks. As I said, each block is a local randomized block, which is a section which depends only on a few bits of the operand of the secret variable. And taking a closer view, we can see that we have some, for example, an S-box circuitry with standard cells, and to the left, we see our randomization mechanism embedded by the tool. So it is all standard, and we get local entropy or local randomization mechanism. Okay, and another nice touch of this countermeasure is that because we are adding it in logic layers in Verilog, any additional countermeasures that we insert into the HDL or on analog layers or any other countermeasures which we have underneath will be protected by this mechanism. So masking, hiding, anything can sit underneath if it is synthesizable. Okay. Now let's discuss this upsizing factor, the bias device, which makes sure that the block receives current always, regardless of the random vector which is assigned to the randomizer. Now, this bias factor is very important because you see there is a parallel connection of resistors, so of transistors, so parallel connection of effective resistors. And because it is a parallel connection, you will get a 1/x dependence. So if you want to achieve a uniform distribution of the leakage, you will need to upsize that bias device. So in this example, we have 4 bits for the modulation. So our security parameter is the number of the randomizer modulating bits, which is denoted by K. So K equal 4. And if we bias this device and increase its size, then we are just traveling on this 1/x curve. And if it is large enough, we will sit on a region of the curve which is quasi-linear. This implies that the distribution of the effective randomness will be quasi-uniform. Okay, so we have a security parameter which we can set to achieve a uniform distribution of the leakage. And our design rule was never to achieve perfect randomization, because then we will need very complex analog circuitry and and the calibration mechanism. So our goal was to achieve a sufficiently uniform distribution, but not perfect. It is okay. Okay, so what we get if we consider the figure on the left is that as we increase our security parameters, K, the number of states of the randomizer, K, then the distribution of the leakage, sigma, increases linearly. However, if we want to stay in the uniform distribution region, the bias device needs to be sufficiently large. So typically, the bias device needs to be 2 at the power of K plus 2. Now, if we compute the SNR in the cryptographic sense versus our security parameter, okay, we can see that as the security parameter increases, the SNR goes down, and that depends, of course, on the noise level which exists in the device. However, we have a scalable construction which gives us security with a security parameter. This is quite new for randomization mechanisms. Okay, so let's look on exemplary leakage distribution. What you see here on the top is a leakage distribution of an unprotected design. So we all know that the leakage distribution of a side channel signal is distributed binomially if the leakages behave like the Hamming weight leakage model, and if the noise is large, then this binomial distribution looks like a normal distribution. And then let's consider our randomization mechanism. And as we go down, we increase our security parameter K. So at the top, K equal to 2, we have 4 states of the randomizer, and at the bottom, K is equal to 5. So we have 32 states of the randomizer. And as you can see, as we increase K, the variance of the total distribution increases. It is not perfectly uniform, but it is a Gaussian mixture with which the lobes of the Gaussian are uniformly distributed. And this is with a small set of measurements. So of course, we did not cover the entire sample space. Okay, so in turn, if we compute the maximum SNR, for example, with K equal to 4, we can see that we can increase the signal to noise ratio by a factor of 10 already with K equal to 4. Now, the area cost of doing that is less than 10% of the logic block it is protecting. So the cost is insignificant. Now, the last point that we need to discuss is that we need to generate randomness, and we need to do that cheaply in order to feed this randomizer. So what we chose to do is to utilize the true random number generator based on a time domain effect. So our goal was to have this randomizer, which is fully standard, possible to implement in Verilog and to embed into our circuit. So what we do is that we sample a very fast oscillator, okay? So oscillator in integrated circuits in ASICs can be very, very fast, and it is being sampled with a slow clock signal. Now, it is being sampled into a shift register, and due to the fact that this fast oscillator is ultra fast, there are hundreds of oscillations in one clock cycle, there is a huge amount of jitter noise accumulated on this signal. And therefore, we are able to sample random values. And these random values are then fed into our randomizer on the top right. And And of course, we can compute again, and we can compute the SNR and the mutual information, and we can show that while increasing the number of states of the randomizer, we do get a significant reduction in the information, in the informativeness of the leakage, or concretely increase the security level. Now, going back to masking, so we all know, we understand that masking is very important, but it is quite hard to use masking by its own because of the quadratic cost. So what you see on the graph is the mutual information, or if you want the security level, is the y-axis, and the SNR, the signal to noise ratio, is the x-axis. And you see here the security curves of three designs: in red, unprotected; in blue, a design protected with 2 masking shares; and in green, a design protected with 4 masking shares. So if we have some security target goal, okay, in orange, then we will need to increase the number of shares in order to reach that goal. And that depends on the baseline SNR that we have in the circuit. So instead of using 4 shares, which is very expensive, we can first insert our randomizer, which reduces the SNR effectively, and then only then choose D to mask. And by that, we can reduce the cost significantly. So, of course, the randomization mechanism that we propose can be also used without masking. It depends on the security level that you want. So these are some results from a 65 nanometer ASIC test chip. What you see here in purple is a leakage distribution of a CMOS design when the randomization mechanism is disabled, and then when it is active. So clearly, our randomization mechanism can significantly increase the variance of the leakage, which in turn reduces the SNR. So you see the switching between a non-randomized circuit to a randomized circuit, between the orange and the green. So a factor of 10. Okay, and we did some calculations and compared to what gains we can get in terms of area overhead to reach a specific security target. So the left y-axis is the security target, so it is this horizontal line, and the green circle on the left will indicate the area overhead of our design with our randomizer mechanism, which needs a D, a number of shares only equal to 5 to reach this security target. However, if we use masking without our randomization mechanism, then we will need 15 shares to reach that security target. And in turn, we will get an area reduction of x10 to x40. So size does matters, okay? And this mechanism is very effective to lower the cost. And the last point that I'm not really going into details about regarding this randomization mechanism is that we embedded a localized countermeasures that needs to help us when the adversary has localization power. You can measure very local signals. So we did some measurements and experiments, and we showed, and we've seen that there is no significant advantage for an adversary, even when he is local, because our randomization mechanism is local. Okay, so I will conclude this part of the talk by an updated version of this mechanism. So just a glimpse of what we are doing now. So what we know with this randomization mechanism is that as K increases, we need to increase also the size of devices in this circuitry with K in the exponent. So we have two devices, the bias and the biggest device, which are 2 to the power of K or 2 to the power of K plus 2. So the cost, the area's cost is exponential with K. This is not really a problem because in real life, already with K equal 4, the cost is very small. And it really depends on the security level that we want to achieve. And especially if we use masking to amplify the noise to achieve security, then we do not really need very large Ks. However, to be complete, we wanted to find a mechanism that is not exponential in the area cost. So in order to achieve that, instead of using the randomizer mechanisms from the previous slide, we can use an R2R duck ladder digital to analog converter. And in this mechanism, you can see that each stage which is affected by one bit is exactly the same size. So one R resistor and one 2R resistor, one R and one 2R. So it does not depend on K, on the number of bits. So the cost of it will be linear with K and not exponential. Of course, that we cannot use this construction as is. We need to adapt it to the power gating mechanism. And we have switches which either connect VDD or connect ground. So we need to utilize both power gating cells and ground gating cells. And then we need to add in the middle this serial resistances with power gating cells again. Now, what we achieve is that we take a digital sequence of bits, and in return, we get VA. It is a voltage level between VDD and ground, which is randomly modulated between the range, uniformly distributed. Now, what we can do is we can add a bias device which will draw the entire voltage closer to ground in order to get this distribution in a smaller range. The reason we want to do that is because now this voltage level, uniform voltage level, will modulate the effective resistance of the circuitry. However, a power gating resistance or any transistor resistance is not uniform, right? The I versus voltage equations of a transistor are typically quadratic. So in order to achieve a uniform distribution, which is best in terms of security, we want to actually modulate it on a small signal level, and then we get a quasi-uniform distribution. So what you actually see here is the randomizer, which is working with that mechanism and randomizing the voltage and the currents of the device. It is very effective, and we can also see here that it is not sensitive to the process corners. So we all know that VLSI process is sensitive to fabrication or manufacturing mismatches. So it is not sensitive to mismatches because power gating cells or ground gating cells are not small. Okay, so this concludes the first part of my talk, and I will fastly move on to the second part of my talk based on work with David Belizia and François Xavier Standard, Ofek Gur, and Tomer Gross. So when we consider masking, we know that we have hardware or parallel masking where a shared value is processed in parallel. So C1, C2, and C3 are processed in parallel. So their leakage is summed up to give us the total leakage. And if it is processed in serial, then each of the bits is computed serially, one after another, and each of the shares is computed in a different time sample. Now, in the parallel construction, we already saw this distribution. If the leakages are summed independently, so the operation is a plus, then we get the distributions as discussed, and then the leakage resides in the second statistical moment, and everything is fine. And in the serial or software implementation, where we have multi-dimensional leakages, then again, everything is fine, and the multi-dimensional leakage only resides in the second statistical moment. However, what I'm going to show is that while playing with the resistance of the power grid of a device, I can affect this plus signal and add a term here which is non-uniform, non-independent. It will, I will add a factor which depends on the multiplication of the leakages. This is a problem for mask designs, as I will discuss. Similarly, while playing with the resistance or the capacitance of the power grid of a device, I can actually make one leakage affect another leakage time sample because the power grid has a large RC effect. This in turn might also make the same effect, that leakages merge non-linearly. Okay, so couplings are electrical, resistive, or capacitive phenomena, which now these capacitive or resistive elements are there in the circuitry. It doesn't matter if we want them or not, they are there. It is electrical constructs that we cannot eliminate. Now, in theory, a leakage of two shares, in theory, we assume this wire is ideal, and the leakage, the total leakage is the summation of leakages. However, once we have those, for example, resistors, the leakages will not be summed up linearly. And this factor depends on many things. They depend on the device, on the technology, if it is software, hardware, FPGA, or application-specific device. What we can do is mainly affect the power grid resistance and the proximity between shares in order to mitigate this effect. The challenge with coupling is they are hard to handle with verification tools. So we have verification tools for masking designs like full verif, mask verif, etc., which handle logical level issues like glitches in masking or composition or transitions issues. They can be detected from the logical representation and be fixed. However, coupling is something which we know about in very late design cycles, and then we need to deal with it with physical layers, post-silicon. And the question is, how does coupling scale with the D, with the number of share of our designs, and how technology-dependent it is? So basically, what we know is that the on-resistance of a share, so the resistance of a logical element processing the shared values, is very small. However, it is much larger than the power grid resistance of a device. However, when we have an external resistor, which is totally in the hands of an adversary, then what we will have is we will get a current flowing to one of the shares, generating a voltage drop across this red external resistor, and this voltage drop will in turn affect the second share. So we get some dependence between the shares on the total leakage. This dependence is turned by a factor of beta, and this factor of beta shows us that we get a multiplication of leakages. And this is the one thing that we are fearing with masked designs, because then our distributions, the leakage will depend on the first statistical moment in this two shares example, and not only in the second statistical moment. So we modeled this behavior, and we've seen that we can either increase the external resistor in order to increase this beta factor, or to reduce the external voltage. And the exploration space for a verification engineer for masked design is quite huge. However, the important point is that we need to be very, very careful when we implement masking designs on physical layers. So what we see here is measurements from a microcontroller, and we did a profiled evaluation. So on the left, you see the same distributions, which are not, where the mean is not depending on the secret. Also on the measurement set, to the left is a model, and to the right is a measurement set. And you see that the mean is not dependent on the secret value. However, when I do have external amplification, so a large external resistor, I do get a bias in the distribution, which means I have information in the first statistical moment of the leakage. So the security order of the design is 2. However, the effective security order goes down to 1. I will move fast on results which shows that it is efficient both on FPGAs and microcontrollers. And I will move on to discuss an evaluation we had for application-specific integrated circuits, so ASICs. And what we wanted to understand is what is more effective, external resistor or the ability of an adversary to affect the leakage from externally to generate coupling, or internal factors like the internal resistance of a power grid or the resistance of logical element in the device. One more question is that we wanted to see if coupling make exploitation of leakage from masked designs effective with larger Ds, with D equal to 3 or D equal to 4. And for that, we built a specialized ASIC, which implements masking constructs, so 2 shares, 3 shares, and 4 shares design, and variable resistors, variable internal resistor, variable external resistor, etc. And what we can see, these are T values, so T-test values, where we want to see in which statistical moment we get a leakage. So this is for 2 shares design. So in the second statistical moment, you see that we are crossing the T-test threshold and we get exploitation. But this is trivial because it is in the second statistical moment. In the first statistical moment, you see that without external amplification, so without an external resistor, we are almost in all cases, so the green curve here, we do not get information. However, with external resistor, we can easily reduce the effective security order of the design and get information with much less traces. Now, this scales nicely also to 3 shares on the top. So with external amplification, we get leakage in the second statistical moment and not in the third statistical moment, which is expected. And also with 4 shares, so the bottom part of the screen. Without external amplification, we only get leakage with the fourth statistical moment with 35 million traces, whereas with external amplification and external resistor of 82 ohms, we can get significant reduction of the number of traces. So only 12 million traces to cross the threshold with the second statistical moment. Okay, so concluding my talk, we've seen that externally amplified coupling induce leakages, which does scale to high order maskings, and external factors, so the adversary controlled factors, are much more dominant, so they are much more dangerous. And in that sense, we need to build design and verification tools to evaluate masked designs in the context of the physical implementation and not only the logical implementation. And in the first part of my talk, I've discussed CAD-compatible, design-agnostic, local and very low-cost hiding countermeasures, which can be used before masking. And interestingly, because they randomize the effective resistance of the power grid, they have the potential to also resist externally amplified couplings attacks, which needs a specific external resistance value. And so, and a nice point about this randomizer is that they come with a security parameter and they are scalable. So thank you, and I will be happy to answer questions if you have any.
Thank you, Itamar, for the excellent talk. It was really very insightful. We would like to open the floor to questions. So if you have any questions, you can raise your hand. We can unmute you, or you can use the Q&A section. So we'll just wait for another 3-4 minutes to see if there are any questions. In the meantime, if I have a question. So in one of the slides, you showed that the WDDL logic performed much better compared to a normal, let's say, CMOS implementation. So is it the effect is due to more of the WDDL, or is it due to the countermeasure which was applied, or is it like a sum?
Yeah, I'm getting to this slide. Not here, right?
Yes, I think it was.
Yes. You hear WDDL?
Yes, this one.
So WDDL behaves nicer from the security perspective because inherently WDDL provides smaller signal to noise ratio. So the signal always look the same. That is the purpose of WDDL. The signal needs to always look the same. So theoretically, the SNR should be 0. However, because nothing can be similar with electronic devices, there are always mismatches. There is some signal difference between the WDDL encodings. And so there is some SNR, some signal. However, it is much smaller than CMOS logic, where the signal is very large. So what you see here, that WDDL reduces by its own the effective SNR by a factor of 10. And then if we build up on WDDL and then use the randomizer mechanism, we can achieve more, okay? However, an important point is that we do not have any security parameter for WDDL. It depends on the technology. So if we want larger security level, there is nothing to be done. But if we do add this randomizer mechanism, then we can always go on and on and on and increase K, and by that, reducing the mutual information or the SNR or increasing the security more and more.
Thank you for the wonderful explanation.